Okay, so last time we're looking at this Floyd Warshall algorithm. We went through the general working principle of the algorithm. So now we'll look at a couple of examples. So before we proceed, just to review what we saw. So we go through iterations. In each iteration, we'll pick a vertex and see whether we can go through that vertex to reduce the shortest path estimate between any two vertices. So which vertex we pick? So we go through iterations and we label the vertices as 1 through n. So in the kth iteration, we pick vertex k. So that means we highlight that corresponding column and row. So let us say I want to now see if we can reduce the entry for cell I comma j. So we have to compare what we currently have at cell I comma j with I plus k. So this is I, when I say I comma j, that means row index I, column index j. So I comma k. So from I to k, this is the distance, and k comma j is this. So from k to j, this is the distance. So the distance from I to k plus the distance from k to j is the sum of these two distances less than the distance that we have currently from I to j. So basically we are trying to go instead of from I to j through whatever the path we know currently, can we go from I to k and then from k to j. So the distance from I to k plus the distance from k to j, is it less than the distance that we know currently from I to j? If that happens, so then we can use this k and go through k. That means now the distance from I to j has to be updated to be distance from I to k plus the distance from k to j, as well as the predecessor on the path from I to j is going to be the predecessor on the path from k to j, because so far we use this path from I to j and the predecessor is a vertex earlier to j on this path from I to j. So now that we are going to go through k and then from k to j, the whatever is the predecessor on the path from k to j, which is say this vertex, is going to be also the predecessor for the path from I to j. Okay, so that's the update we have to make. So if we cannot reduce the distance, so that means if the distance from I to k plus k to j happens to be more than the distance that we know from I to j, then we stay with what we know from I to j, just stay that path. We don't update to go through k. So that's what we're going to go through in each iteration. So now to update the predecessor, this is what as I said, the distance predecessor, if I decide to go through k, then the predecessor on the path from I to j is indicated here, and we are going to update that to be what? Whatever is the predecessor on the path from k to j is also going to be a predecessor on the path from I to j. Okay, so we are going to just look at row k and the column j. So whatever is the predecessor on the path from k to j, that vertex id is going to end up to be the predecessor from on the path from I to j. Okay. Alright, so let us go through this example now. So I've given you here a graph as a directed graph with edge weights. So your first step is to come up with the two matrices, a distance matrix and the predecessor matrix. So the distance matrix for the diagonal, unless you have a self loop, means from a vertex to itself from 1 to 1 or 2 to 2 and so on, unless you have something like that, to begin with, the diagonal will always be 0. Okay, so that also means from a vertex to itself, the length of the shortest path, means the distance of the shortest path, is going to be 0. Now to the other vertices, if you have an edge, then that edge weight is the distance you have, and here you have directed edges. So from 1 to 3 you have an edge, so the distance from 1 to 3 is 3. And in the predecessor matrix, if you have an edge say from 1 to 3, then on the path from 1 to 3, vertex 1 itself is the predecessor, because in order to reach 3 you have to reach 1, and that 1 itself is also starting vertex. So from 1 to 3, that's the predecessor. Now if you don't have an edge, Now there's a question, does Floyd Warshall work only for directed graphs? No, it could work for any graph. It could work for both undirected as well as directed. Okay. Now I pick directed because that will clearly explain all possible cases that we need to handle. Okay. All right. So if there's no edge, like in this case, there's no edge between say what 1 to 2, right? So there's an edge from 2 to 1, but there's no edge from 1 to 2. So the distance is infinity, because we don't know currently a path from 1 to 2. So that's why I said the distance is infinity. And the predecessor is not known because we don't know the path either. So we just said the entry as null or not applicable. Similarly, for the diagonal, we can set it as not applicable. Okay. So that is how you fill up the distance matrix and predecessor matrix. So another case, so if you have an edge from 2 to 1, so on row 2 column 1, that's what I comma j means, a row from I to j. So the distance is 2 and predecessor is v2 itself, and 2 does not have an edge to any other vertex, so it is infinity for 3 and 4, and then not applicable as a predecessor for 3 and 4, and 2 to itself is 0, and the distance and the predecessor is not applicable. Okay. Alright, so let us now go through the iterations. So in the first iteration means we are considering to go through vertex 1 for all the possible shortest paths. So that means we'll highlight row 1 and column 1. So we are going to use the matrix that we got from the earlier iteration. So that means in this matrix we are going to highlight the column 1 and row 1. That's what I have done here. So we are going to explore whether we can reduce the entries we have for the other cells here, which are shown here. Similarly, so since this row and column, it's not going to be changed in this iteration corresponding to vertex 1, the entries in the predecessor matrix corresponding to that row and column will also not change. So we can write down the entries for the column and row for vertex 1 as it is, because they are not going to change. And make sure you also kind of highlight that row 1, because that's that vertex row k, using which you are going to update the predecessors if any of the estimated values change here. So remember here, we have to use that row k, and whatever is the predecessor on the path from k to some vertex j, we have to set that as also the predecessor on the path from I to j. Okay. Alright, so let us go through this. So here for 2 to 2 it is 0 currently. So we have to explore whether there is a path from vertex 2 to 2, vertex 2 of weight less than 0. So for that, what we have to do is we have to explore again by going through vertex 1, because this is iteration 1. So as I said last time, you can simply draw a horizontal line that hits the highlighted column and a vertical line that hits the highlighted row. So if you do that from this cell 2, 2, it will hit this cell, so that's 2, and it will hit here as infinity. So these are the distance now from, so V2 to V1 is 2, plus from V1 to V2 is infinity. So we are going to go through from vertex 2 to vertex 2 through vertex 1. So vertex 2 to vertex 1 is 2, the distance, and from vertex 1 to vertex 2 is infinity. So is 2 plus infinity less than what we know currently for vertex 2 to vertex 2, which is 0. So 2 plus infinity is infinity, not less than 0. So we'll stay with what we know currently, so that's why I say this is 0 here. Okay. So the next slide, actually I show all the updated values. So here we'll just use this for practice. So since I did not change this entry here, we are going to just stay with not applicable here, right? Now what about this cell? So we are trying to fill this cell 2, 3. So that means I should draw a horizontal line as well as a vertical line. So the horizontal line will hit here at this value 2 and the vertical line will hit at 3. So I'm going to add 2 plus 3. So 2 plus 3 is 5. Is it less than what we currently have for cell 2 comma 3? Currently we have infinity as a distance from vertex 2 to vertex 3. And now by going through vertex 1, we find out the distance to be 2 plus 3, 5, which is less than infinity. So I can update this entry to 5, and the corresponding entry here should be whatever is from V1 to V3, which is V1 itself is the predecessor. So I put V1 as the predecessor here. Again, that's because simply this. We want to update the entry for I comma j. We found out to be like 2 plus 3 is going to be 5 less than infinity. So we update that to 5. And so on the path from I to j, we are going to use as part of the path from I to j, we are going to go through k, right? So whatever is the predecessor on the path from k to j, that's also the predecessor for I to j. So that means whatever is that predecessor from V1 to V3, which is V1, is also going to be the predecessor from V2 to V3. That's V1. Okay. So if you cannot stop and ask me if you have any questions. Now let us fill this entry. Have infinity. So again we draw a horizontal line. It reaches here at 2. The vertical line reaches this highlighted row at infinity. So 2 plus infinity is still infinity, not less than what we know currently, which is also infinity. So we will just put that infinity here and retain whatever we have for the cell. So it's not applicable, so it's not applicable here. Okay, so let us now try to fill this cell. Currently we have 7 as a distance from V3 to V2. So we have to see if we can do better than less than 7. So highlighted, if you try to draw a horizontal line, it goes here at infinity and touches here at also infinity. So infinity plus infinity is infinity, not less than 7. So we stay with 7 as the distance, and V3, whatever the entry here we have, is same as we'll put that here as a predecessor. Now here it is 0 as the distance from V3 to V3. We have to check it, can we do less than 0. So again the horizontal line will reach here at infinity, vertical will reach here at 3. So is 3 plus infinity less than what we know currently for that entry, which is 0? The answer is no. So we will stay with 0, and that's not applicable here. Now we are trying to see if we can do less than 1. So again the corresponding entries we have to add are infinity, and then vertically it's also infinity here. So infinity plus infinity is infinity, not less than 1. So we'll put that 1 here and stay with V3 as the predecessor. Now let's fill the last row here. So this cell currently is infinity. So we have to see, can we do less than infinity? So if we draw a horizontal line, it will hit the highlighted column at 6, and the vertical line will reach here at infinity. So infinity plus 6 is still infinity, not less than infinity. So we'll stay with infinity, and this is not applicable here. Now for this cell, the highlighted row will hit at column will be 6, and then this will be 3. So 6 plus 3 is 9, less than what we currently have, which is infinity. So that means we can put 9 here, and the predecessor entry that we're going to have here is same as going to be what we have for row 1, V1, corresponding column V3, because you're trying to fill this cell from V4 to V3 by going through V1. So look at that row for V1, and what is the predecessor to reach V3? The answer is V1. So just put that predecessor V1 here as the predecessor from V4 to V3. Okay. Now for this cell it is 0 so far. Can we do better than 0? Draw a horizontal line, reaches here at 6, vertical at infinity. So 6 plus infinity is infinity, not less than 0. So we stay with 0 and put not applicable here. So that is how we fill the entries in an iteration. Okay. So this is for first iteration. So now we will make use of this updated distance matrix and predecessor matrix to do the second iteration. So in the second iteration, we have to highlight, that means second iteration means you are trying to go through vertex k between any two vertices for a shortest path. So we'll highlight the column 2 and row 2 that we have at the end of this first iteration. So I have highlighted, this is what we have at the end of the first iteration for the distance and predecessor matrix. So I'll highlight here the column 2 and vertex 2. So that's what is given here. So we have to try to now fill the other cells. So let us do the process. So currently from V1 to V1 is 0. So we have to see, can we do better than 0? So again, if you draw a vertical line, it reaches the highlighted row at 2, and a horizontal line will reach the highlighted column at infinity. So we are going to see 2 plus infinity is less than 0. The answer is infinity, so it's not less than 0. So we'll stay with what we know is 0, and the highlighted and the predecessors, whatever it is, not applicable in this cell. Only if you change an entry in the distance matrix, you have to update the entry in the predecessor matrix. Now also in the predecessor matrix, you highlight this or write down the entries we have from the previous iteration for this row, column 2 and row 2, because we are not going to change the distance values we have for row 2 and column 2. So the entries in the predecessor matrix for row 2 and column 2 are also not going to change. And we highlight this row 2 because we will make use of these entries we have in row 2 to update the predecessors for the other entries if you change the distance. Now currently we have for this cell from V1 to V3 the distance is 3, so we have to see, can we do less than 3? So to decide that, add the corresponding values in the highlighted row and column. So if you draw a horizontal line, it reaches here at infinity. A vertical line reaches here at 5. So that those are distances. So for example, here you're going to trying to find the distance from V1 to V3 by going through V2 in iteration 2. So this entry indicates the distance from V1 to V2, and this entry indicates the distance from V2 to V3. So V1 to V2 is infinity, V2 to V3 is 5. So that's what I mean by picking the highlighted row and cell, corresponding cell in the highlighted row and column. So infinity plus 5 is infinity. That is not less than what we know currently as a distance from V1 to V3. So we stay with what we know currently from V1 to V3, which is 3. And write down what we have the corresponding predecessor, which is V1 for that cell. Now the distance from V1 to V4 is currently infinity. Now if you go through V2, it's going to be V1 to V2 is infinity, V2 to V4 is also infinity. So infinity plus infinity is infinity, not less than infinity, so we'll stay with infinity and not applicable as it is from this entry. Now for this cell here, we have from V3 to V1 is infinity, so we have to see, can we do better than that? So if you draw the horizontal line, it is 7, vertical it's 2, so that means the distance from V3 to V2 is 7 and V2 to V1 is 2. So 7 plus 2, 9 is less than what we know as the distance from V3 to V1, 9, which is infinity. So we can update this to be 9. So since I'm going to go through V2, look into the row for V2 and see what is the predecessor to reach from V3 to V1. So from V3 to V1, that's the cell we are updating. So look what is the predecessor now from V2 to V1. Okay, so that's going to be V2. So we are trying to go through V2 to reach V1 from V3. So from V3 to V1, we are trying to go through V2. So, and we decided to go through V2 by making it 9. So that means we have to see what is the predecessor to reach from V3 to V1. The predecessor is going to be same as the predecessor from V2 to V1. So that's going to be V2 in this cell. So that's what we enter here, which is V2. Now for this cell, currently we have 0. So we have to decide whether we can do less than 0. And for that we have to add the highlighted row and column cell corresponding. So if you draw a horizontal line, it reaches here at 7 and this will reach here at 5. So that means V3 to V3 to through V2. So V3 to V2 is 7, V2 to V3 is 5. So the sum 5 plus 7 is 12, not less than 0. So we stay with 0, and whatever is the predecessor we have here which is not applicable, we write down here. Now for V3 to V4 we currently have 1 as the distance. Now if you draw the horizontal vertical line, it is 7 and infinity here. So 7 plus infinity is infinity, not less than 1. So we stay with 1 and write down whatever is the predecessor, which is V3 here. Okay. Now for this cell from V4 to V1, we have to add the highlighted row values 2, and then this is infinity here. So 2 plus infinity is infinity, not less than 6. So we stay with 6, and V4 is the predecessor. Now for this cell, currently the distance is 9. So draw a vertical line, reaches here at 5, horizontal line reaches here at infinity. So 5 plus infinity is less than 9, no, so stay with 9 and have V1 as the predecessor. Now currently it is 0, and if you go through V2 it's going to be infinity plus infinity, so it's still infinity, not less than 0. So write down 0 and not applicable. What are the entry we have here is the same here. So that is the distance matrix and predecessor matrix at the end of the second iteration. Okay. Now, so we use that distance and predecessor matrix to go through the third iteration. So in the third iteration means we are trying to go through vertex 3. So highlight the column and row corresponding to vertex 3, so that we have at the end of the second iteration. So these are the entries we have at the end of second iteration. Now we're trying to fill the matrix for third iteration. So since the column and row are not going to change, the corresponding predecessor column and row are not going to change either. So write down whatever we have from the predecessor matrix in the end of the second iteration. Also highlight the row corresponding to vertex 3, because these are the entries we're going to use as the possible predecessors if you're going to update any entry in the distance matrix. Alright, so by now you should have figured out the diagonal, say V1 to V1 or V2 to V2, they are going to change only if you can reduce something less than 0, right? So it is possible to reduce the distance to something less than 0 only if you have at least one negative weight edge in the graph. So as a clue, if the graph assigned to you does not have negative weight edge, you can always be confident that the distance from a vertex to itself is always going to be 0. It's not going to go less than 0. So you can also fill up those entries, the diagonal entries, to be zeros if your graph does not have negative edge weight. So later we'll walk through one more example where it might be possible that we could reduce the distance from a vertex to itself to be something less than 0. Okay. So in this case, we are not going to have that because all the edge weights are positive. So we can right away write the distance to be 0 from vertex 1 to 1, on vertex 2 to 2 is also 0, vertex 4 to 4 is also 0. Of course, you can always cross check. How can you do that? Draw the vertical line and horizontal line, so to highlight the row and column. So that will be 3 here and going here to 9. So 9 plus 3 is 12. Not going to be less than 0. So that's why I say you can put 0. Now what about this entry from vertex 1 to 2? So currently we have infinity as the distance estimate from 1 to 2. So you have to see, can we do less than infinity? So again, draw a horizontal line and vertical line to the highlighted row and column. So it will be 7 vertical and horizontal is 3. So 3 plus 7 is 10 and it's less than infinity. So we put 10 here. So we have to now change the predecessor entry in the cell. So for that we have to look at this row for V3, and so we are trying to fill the entry from V1 to V2 by going through V3. So we found out that by going through V3 gives you a lower distance. So that is why the predecessor for V1 to V2 is same as the predecessor from V3 to V2. So from V3 to V2, the predecessor is V3. That's what this matrix tells us. So make this V3 also as a predecessor from V1 to V2. That's the predecessor from V1 to V2. So you can update that entry as I show here. So now this entry is infinity from V1 to V4. So if you're now going to V3, it is from, you have to highlight the row and column. So the horizontal line will reach here at 3, vertical line will reach here at 1. So that is going to be 3 plus 1. You can always cross check or interpret what it really means. So we are trying to go from V1 to V4 through V3. So from V1 to V3 the distance is 3, and from V3 to V4 the distance is 1. So 3 plus 1, that's why we add the distance 3 plus 1. 4 is less than infinity, so that's better to go through V3. So we make it as 4 here, and so we have decided to go from V1 to V4 through V3. So the predecessor is going to be whatever is the predecessor from V3 to V4. So V3 to V4, the predecessor is V3, so we make that also as a predecessor here from V1 to V4. Okay. Now this cell from V2 to V1 is currently 2, the distance from V2 to V1. Can we do less than 2? So we have to find the highlighted row and column. So it will be 9 vertical, and horizontal is going to be 5. So 5 plus 9 is going to be 14, not less than 2. So we stay with 2, and whatever is the predecessor we have, which is V2, you have to write the same predecessor V2 here for that cell. Okay, so now it's again diagonal V2 to V2 is 0 because this graph has only positive edge weights. You can always cross check. The vertical line will reach here at 7, horizontal will reach here at 5. So again 5 plus 7, 12, less than 0, no, so stay with 0, and the whatever is the predecessor not applicable will be the predecessor here. Now this entry is infinity now as a distance from V2 to V4. We have to see if we can do less than infinity. So draw a horizontal line to the highlighted column. It will be 5, and this will be 1. So that is the distance from V2 to V3 is 5, and the distance from V3 to V4 is 1. So 5 plus 1, 6 is less than infinity. So we can make it 6. So again we decide to go through V3 to reach V4. So V3 to V4, the predecessor is V3. So write down the same V3, this V3 here, as what was the predecessor entry, as the predecessor entry here from V2 to V4. Now this entry from V4 to V1 is 6. We have to see if we can do less than 6. So draw a vertical line, it reaches here at 9, horizontal reaches here also 9. So 9 plus 9, 18, not less than 6. So we stay with 6. And what are the entry here for this cell in the predecessor matrix, which is V4, we stay with V4 here also as a predecessor. Now this entry is currently infinity, so the horizontal line will meet here at 9 and the vertical at 7. So 7 plus 9 is 16, less than infinity. So we make this as 16, and the predecessor is going to be on the row V3. So this is from cell V4 to V2. So you have to look for the predecessor in the row V3 to V2. The predecessor is V3. So write down that as a predecessor for V4 to V2. So for V4 to V2, the predecessor is V3. Now this cell is going to be 0 because it's V4 to V4, it's a diagonal, and we have all positive edge weights. So that is the matrix, the end of the third iteration. So now we have to go through the fourth iteration, which is the last iteration, because you have 4 vertices. So in Floyd Warshall, there is no way to optimize. You have to go through all the 4 iterations. Okay, so let us continue. So in the fourth iteration, we are going to go through vertex 4. So we highlight the row corresponding to vertex 4 and the column corresponding to vertex 4 in the distance matrix. And similarly highlight the row and column in the predecessor matrix, and also you can again circle the cell row V4, because these are the entries in the predecessor matrix we are going to use to update the predecessor entries here. Alright, so again we can write all the diagonals to be 0 because again positive edge weights, So let's check now. From V1 to V2 it says 10 here. Can we do less than 10? So for that, draw the horizontal line, which is 4, and the vertical line is 16. So 16 plus 4 is 20, not less than 10. So we stay with 10 as the distance from V1 to V2, and V3, whatever is the predecessor entry here, it will also be the predecessor entry here, V3. Now the distance from V1 to V3 is currently 3. Can we do less than 3? So the vertical line will reach here at 9, horizontal at 4. So 9 plus 4 is 13, not less than 3. So stay with 3, and the predecessor entry is V1. So that's V1 here. So that's what we have to do for the other entries. So it is 2 here. Now 6 here, and horizontal vertical is also 6. 6 plus 6 is 12, not less than 2. So we write down 2. And this corresponding entry V2 is also written here. Now for this V2 to V3 is 5. So the vertical will be 9, horizontal is 6. So 9 plus 6, 15, not less than 5. So stay with 5. And V1 as the predecessor. Now let us try here. Currently we have 9 as a distance from V3 to V1. So the vertical will be 6, horizontal 1. So 6 plus 1, 7 is less than 9. So this is where we can, scenario where we can change, reduce from 9 now to 7. So again, this is from V3 to V1 by going through V4. V3 to V4, the distance is 1. V4 to V1, the distance is 6. So V3 to V4 plus V4 to V1, 1 plus 6 is 7. Less than 9, so we can make it 7, and so we're going from V4 to V1, right? So V3 to V4 and V4 to V1. So look into the row for V4 to V1. The predecessor is V4. So put that as a predecessor now to reach from V3 to V1. So V3 to V1 going through V4. So from V4 to V1, what was the predecessor? The same as the predecessor now going from V3 to V1. So that's V4. So that's what you will update as the predecessor. Okay. So now this entry here is 7. So if you try to reduce it, it is vertical is 16, horizontal is 1. 116 plus 117, not less than 7. So stay with 7. And that entry V3 is also written down here as a predecessor, and this is V3 to V3, a diagonal entry. That's not going to reduce further. Alright, so we have gone through all the 4 iterations, and that is the final distance and predecessor matrix. So the entries here basically indicate the shortest path weight from a vertex to another vertex. So this is all paths shortest path. So between any 2 vertices, or from one vertex to another vertex, because this is the directed graph. So let us try to go through a couple of cases how to identify the path between the from one vertex to another vertex. So let us say from V2 to V4, the distance is 6. So what is a path from V2 to V4 in this graph of distance 6? So for that we'll make use of the predecessor matrix. That's why we recorded that so far. So from V2 to V4, it says the predecessor is V3. So that means if I want to go from V2 to V4, I have to first go from V2 to V3 and then take an edge to V4. That's what it means. So V2 to V4, the predecessor is V3. So that means we have to now find out what is the predecessor from V2 to V3. So from V2 to V3, it says the predecessor is V1. So to go from V2 to V3, I have to first reach V1 and then go from V1 to V3. So now from V2 to V1, it says the predecessor is V2 itself. So that is the edge from V2 to V1. So this is now the path from V2 to V4. Again, it's not necessarily that you have to have all the other vertices as intermediate vertices. Like you see here, this is a graph of 4 vertices. We are trying to reach from V2 to V4, and in this example it ended up like V1, the other 2 vertices V1 and V3 are the intermediate vertices, but it need not be always the case. It could be you can directly go from V2 to V4 or just use one intermediate vertex and so on. So it depends on the graph and the edge weights. Okay. So now from V4 to V2, V4 to V2 you have here the predecessor is V3. So from V4 to V2 we have to first reach from V4 to V3 and then take an edge to V2. So now we have to know how to reach from V4 to V3. So V4 to V3 it says V1 is the predecessor. So V4 to V3 you have to first reach from V4 to V1 and then from V1 to V3 we can take an edge. So now from V4 to V1 the predecessor is V4 itself, so that means we have an edge from V4 to V1. So that's the path. Now again you can cross check for the edge weights. So like let us do for this path. So V4 to V1 the edge weight is 6. Then V1 to V3 the edge weight is 9. So 6 plus 3 9 so far, and V3 to V2 the edge weight is 7, which is 16. So that's the shortest path weight from V4 to V2. Okay. On this one from V2 to V1 it is 2. Then V1 to V3 it is 6. And V3 to V4 it is 1. So 2 plus 3 plus 1, 6. That's the shortest path weight from V2 to V4. So we can cross check whether you identify the right path. Now again let me just reiterate what we went through. So we go through 4 iterations in this example because we have 4 vertices. Again, from the fundamental principle of Floyd Warshall, in iteration 1 we are trying to go through vertex 1. That also means we are trying to consider only vertex 1 as a possible intermediate vertex. In iteration 2 we are trying to go through vertex 2, but that also means we make use of the results from iteration 1. That means we have considered also the earlier vertex, vertex 1, and we are now trying to see can we also make use of vertex 2 as a possible intermediate vertex. So at the end of the second iteration, whatever the distance values we end up with or the best possible distances that we can have between or from one vertex to any other vertex, by considering only vertices 1 and 2 as the possible intermediate vertices. So that means also at the end of iteration 3 what we have is the shortest path distances possible from one vertex to any other vertex by considering only vertices 1, 2 and 3 as the possible intermediate vertices. Like you see at the end of iteration 3 we have distance 9 as the distance from vertex 3 to vertex 1. That means that is the shortest possible distance we can have from vertex 3 to vertex 1 by considering only vertices 1, 2 and 3 as the possible intermediate vertices. Then in the 4th iteration we are able to reduce that distance from 9 to 7 by considering vertex 4 as a possible intermediate vertex. So when I say the distance from vertex 3 to vertex 1 is 7, that means we have considered at the end of the 4th iteration, that means we have considered all possible combinations, either vertex 1 or vertices 1 and 2 or just vertex 2 or vertices 1, 2 and 3 or just vertex 3 or vertices 2 and 3 or all possible combinations of vertices 1, 2, 3 and 4. And among all those combinations, whatever I considered, the shortest path weight you can have from vertex 3 to 1 is 7. And the vertex 4 is the predecessor, and of course you know as by just what we did, once we identify one predecessor then we can reach from V3 to V4 using that entry from V3 to V4 whatever we have. Okay, so that's something you have to understand for Floyd-Warshall algorithm. So at the end of the 4th iteration, when I say this is a distance matrix, that means that is the shortest possible distance we can arrive by considering all possible combinations of vertices 1, 2, 3 and 4. And this is the combinations. For example, from V2 to V4, this is the combination we have to choose for a shortest path distance. From V4 to V2, this is the combination that we have to choose for a shortest path distance. For any other case, say from V3 to V4, it says V1 is the distance. That means from V3 to V4, the predecessor is V3 itself. That means just go on the edge from V3 to V4. That is the shortest path distance. Okay, we don't have to really consider the other two vertices as intermediate vertices. So it really depends on the graph and the edge weights. And this is the general principle. So at the end of each iteration, at the end of the kth iteration, you are really considering all combinations of vertices from 1 through k as the possible intermediate vertices. and it could be that you don't need to have an intermediate vertex, like in the case from V3 to V4. Okay, so I hope this is clear. This is the working of Floyd-Warshall algorithm. So let me save this video. If you have any